The next speaker is going to be Jinsen, who is a PhD student in the machine learning group.
Okay, so can everybody hear me? So it's my great pleasure to be presenting here the second time. So I'm Yingzhen, and I'm a final year PhD student, and I work with Rich Turner. So today I'm going to talk about a recent work that we submitted to the ICML that is called Approximate Inference with Amortised MCMC. So this is also a joint work with Chang Liu at Dartmouth College. So this work is actually very much in line with what Sebastian has talked about, but Sebastian has rushed too quickly, so I hope I can explain things a bit more clear about it. Okay, so let's talk about Bayesian inference. I hope many people here do Bayesian inference. So Bayesian inference, the main key part of Bayesian inference is basically you want to integrate out the unobserved variables in your model. So these unobserved variables, for example, can be the latent variables in a generative model or the weight matrices in a Bayesian neural network. So I've written some papers in approximate inference, and this is basically the sentence I usually include in my paper, that we do approximate inference because exact inference is intractable. And what intractable means here is basically we can't compute the integral we want in, within the computational budget we have. But now I would invite you to think about this question. So what does tractability really mean for an approximate inference algorithm? So maybe this question sounds a bit silly, but I think throughout the reasoning of these questions, you can actually see what you really want and what kind of constraints presented when you want to design an approximate inference algorithm. So let me be a bit more precise about that, just to set out the math. So usually in Bayesian modeling, we define our model to start with. So we have a prior on the latent variable z, and also the likelihood time p of x given z. So we usually interested in the exact posterior, which is here given by the Bayes rule. So the reason why we are interested in the exact posterior is basically we want to do inference. And here, what inference really means is basically given some function f that you are interested in computing the kind of some quantities, you actually want to compute the expectation of that functions under the exact posterior. So let me give you two examples. So the first example will be the predictive distribution. For example, in Bayesian neural nets, after you observe a bunch of data, you want to compute the posterior and then use the posterior to predict the kind of the results on unseen data. So this is done by the predictive likelihood, computing like this. Or if you actually want to evaluate the posterior itself, you can basically just take f as the indicator function. So then compute this integral, then you get back to the exact posterior. So we said that the posterior, the exact posterior, is difficult to compute. We cannot compute that in an efficient way. So instead, in approximate inference, we usually find a simpler distribution queue in some kind of tractable family curly queue, such that the proposed approximation approximates your exact posterior in a good way. So after you've done that, you can basically do inference by approximating the integral you actually want with the expectation of your function f in interest under the approximate posterior queue. So I hope this is a very clear setup, and this brings in the kind of the main constraints or the main requirement for you to design approximate inference algorithm, which is the fast computation of the right-hand side term. So hopefully this is kind of easy for you to grab, and I think when we designed approximate inference algorithms, this is the main constraint, and actually I would actually want it to be the only constraint when you design approximate inference algorithms, because if that's the case, you can actually use very flexible Q distribution to construct a very flexible approximation, and hopefully that would be a very accurate approximation to your exact posterior. Then you can get a kind of good approximation to the integral you actually want. But in fact, right now, most of the available approximate inference algorithms actually has more constraint than that. So for example, let's talk about variational inference. Many people should be familiar with that. So in variational inference, you usually optimize a Q distribution in some family using the variational law bound depicted here. So here you have a reconstruction loss and also the entropy term for your Q distribution. So in the old days, people used mean field, but now we are not happy with mean field because usually we have more complicated data and also have very complicated P distribution, so the posterior will be very complicated. So, and then we want kind of like a powerful Q distribution. So now people have normalizing flow, invertible transformation, etc. So, but those distributions, this expectation is no longer computable in an analytical way. So instead, we will do multi-color approximation. Basically, you take samples from Q and then compute the empirical average of this term and maybe also for the entropy term as well. So after you've done training, so you've got some kind of Q distribution, then again, you will do the inference task by basically taking samples from your Q distribution and then compute the empirical average over your samples from Q that basically produce an approximation to the integral you want. So this is nice because we can use sampling to approximate a thing, and here it kind of implicitly assumes that it is easy to sample from Q. That is aligned with our previous assumption. But now you actually have one more constraint for the variational inference, because here, when you're actually optimizing your Q distribution according to the variational law bound, you need to be able to compute the entropy term. So even when you do multi-color approximation, you still need to evaluate the log density at the samples you get. So this fast density at evaluation kind of constraint actually comes from the entropy term here. But also one more thing we noticed that after optimization, so once you've trained your Q distribution, in inference time, you don't actually evaluate the density. So that basically says that this kind of requirement only comes from the optimization procedure. It is not really required by the inference procedure itself. It only comes from the optimization. So that looks a bit bad, comparing to the previous kind of constraint we want. So let's look at another class of approximate inference methods, which is MCMC. So some people might disagree that this is an approximate inference algorithm, but I would say it is only exact when you actually simulate it for infinite amount of time. So when you actually simulate with finite amount of time, I would still consider that as a kind of approximation. So MCMC is actually very simple. So you first define a transition kernel, curly K, that leaves your exact posterior invariant. So often this curly K transition kernel can be very easy to simulate. And then you just need to pick a kind of initial distribution where you draw your initial positions and then run T-step MCMC. You get the samples from your Markov chain. After that, you basically use these samples to construct the approximation to the integral you want. So in this case, it is actually very simple because you just need to be able to run these kind of transitions, i.e. simulate samples from your transition kernel. But then, as I said before, for MCMC, you usually need to run it for a very long time in order to get a kind of accurate approximation. So inference is typically very slow when you actually run it for a very long time. So before I present the algorithm, let me just give you a comparison between these two classes of methods. So we have variational methods here, we have MCMC methods here. The advantage is noted in the kind of green text, and the disadvantage is noted in the red text. So what I want to emphasize here is basically you can see that the disadvantage of one side is pretty much the advantage of the other class. So for example, I already said that in variational methods, you need to evaluate the density because you want to optimize your density. But the MCMC, you just need to be able to simulate your Markov chain dynamics. So variational methods, often the people say that it is less accurate. MCMC is more accurate. But the accuracy of MCMC is in the price of, long simulation times because you need to run the Markov chain very long time. But for variational inference, once you've trained your Q distribution, you can do inference very fastly. But one more kind of problem is it in MCMC. It's basically the samples are not reusable. So for example, in some cases where you want to learn a latent variable model by doing maximum likelihood, you need to do inference on the latent variables. So if you do MCMC on that, then you need to collect the MCMC samples, compute the integral you want, and then update your model P. But once P is updated, you just need to throw away your MCMC samples and run the MCMC methods again on the new updated P distribution, which means you need to start your MCMC again, and it takes a long time. So for variational inference, it is another story. We all know that we have the variational autoencoder method that basically amortizes the inference. So we don't need to basically restart training our approximate distributions from scratch. We can basically do a kind of encoder-like things and amortize the inference. So basically, in this one, amortized MCMC, I'm trying to solve this problem, basically trying to make the kind of samples reusable in some sense. But it turns out that during the kind of the investigation of this problem, we actually figure out another strategy to remove the fast density evaluation requirement in variational methods. So let me just go to the details. But before the maths, I think if you don't want to remember math, this is the only slide you want to remember. So our goal here is to basically train a sample generator that can approximately get samples from your example stereo. So how will we train that? So basically, we first let a sample generator to generate some samples and then present these samples to a teacher model. So the teacher will basically see whether these samples approximate your posterior well or bad, and then basically trying to improve the samples from the generator by running MCMC starting from your samples. And after that, we arguably have a kind of better set of samples, and then the generator will try to figure out how to generate those better samples. So we then loop this kind of procedure many times until the time when the teacher cannot improve your samples. So when that is reached, your sample generator has reached the kind of stationary distribution of the MCMC algorithm, which is the example stereo. So just be a bit more precise. So in this kind of method relies on two assumptions. So first, you have a MCMC kernel that has a unique stationary distribution, which is your example stereo. And when you simulate your MCMC methods very long time, it will actually converge to the stationary distribution you want. These two assumptions are very kind of, normal assumptions required by MCMC methods, so it's reasonable to assume that these hold. So then under these assumptions, you can basically see that for all t greater than 0, so t is the number of steps you want to simulate for your MCMC methods, your initial distribution equals to the distribution after the MCMC steps, if and only if your initial distribution equals to the stationary, which is basically your example stereo. So that basically says if you have some methods to match your initial distribution to the distribution Qt, that is the sample distribution after t-step transitions, then you are done. So just to summarize the kind of ingredients in our framework, so this is like a student-teacher-like method. You have a student, which is basically an architecture of the initial distribution that you can basically generate samples from it. And you can also do kind of a teacher model, which is basically a transition kernel that will simulate the MCMC moves, and also a feedback loop, which tells you how to match the initial distribution to the distribution after t-step transitions. So for these parts, we often propose some kind of divergence or discrepancy measure here, but here it also notice that Qt is also a function of the initial distribution. So that means you need to differentiate through your Qt, which makes things a bit messy. So instead, we propose a kind of projection-based update, which basically says, okay, giving me a set of candidate distributions. I want to find the best distribution that approximates the QT the best. And in this case, we fixed QT as some kind of, you don't actually compute gradients through QT. So in this case, if you think this projection step is very hard, you can even do one more approximation, like one gradient step approximation projection, basically just like doing chain rule, doing gradient descent here. So I think through this kind of approximation, it can basically remove the problem of vanishing gradients in QT, and then you can do gradient descent here. But there is one more gradient ingredient that is missing, which is the selection of the divergence. So in principle, you can actually choose any divergence you want. But as I mentioned before, I want to remove the constraint of fast density evaluation, which leads me to choose kind of like GAN-related methods. So in this case, we already assume that your sample generator can easily generate samples, and also you can run MCMC dynamics to generate samples from QT. Then you can basically, try to use these two sets of samples to estimate the divergence you want. For example, like the Jensen-Shannon divergence here, where you have a discriminator, and then feed in these samples to the discriminator can compute an estimation of this divergence. So I think this is pretty much the same idea that is used in Sebastian's adversarial VV paper. But I also want to mention that we can also use some other methods like FGAN, MND, or vast distance, because we are not minimizing KL. We are not limited to minimizing KL. So by doing this, we actually remove the fast density evaluation requirements. So that tells you for this algorithm, the only requirement is basically fast sampling from your initial distribution and also the transition kernel. So that sounds good. So one more thing we can get from this framework is to do approximate maximum likelihood with MCMC. So remember, in VAE, we kind of jointly optimize the variational lower bound with respect to the model parameter theta and also the Q parameter phi. But it seems like here the dependencies to the model parameter theta comes from this reconstruction term, so this term plays nothing with it. So instead, in amortised MCMC, we already have samples from QT. We can also use QT as an approximate posterior. And this leads to the stochastic EM-like algorithm, which optimizes the variation parameter phi with amortised MCMC, and then use these samples from amortised MCMC, basic sample from QT, to compute the objective function for the model parameter theta. So this is basically the whole algorithm. Let's just see some results. So I'm testing these things on generative models on MNIST. So this is basically the model structure. It is a pretty small model. I'm just using it trying to align with the literature. So we consider three types of Q distribution here. One is just the Gaussian case, which is just what you use as default in VAE. Another two models are basically just like neural networks that warps random noise, and in the CNG models, we warp the Gaussian noise. In the CNB models, we warp Bernoulli noise in a way which is pretty much like a dropout. So the MCMC methods we use here is the Langevin dynamics without rejection. I also try rejection methods as well, but it seems without rejection, it will just learn a bit faster. So I'm basically just showing you some kind of samples from the models. So I'll basically say that they are of similar kind of visual quality. But we also consider some quantitative evaluation as well. So the first evaluation we consider here is the missing data imputation task. So basically you have the digits here. You basically remove the pixels in the lower half of the image, and then you want to use your model to impute back the kind of missing pixels. So we've done this by an approximate deep sampling procedure, which loops through these two steps. So you first get a kind of representation from your current imputation result, and then do a reconstruction, and then put in the reconstruction pixels to your mixing points. So I'm showing you the kind of imputation results for every 2 time steps. So you can basically see that Gaussian, you often collapse to one solution. But for our methods, you have diverse solutions, and even for this method. So you can basically see that, for example, the last line here, for the imputation for digit 9, we can actually get back to answers like 2, 0, 9, 8, and 3, something like that. We quantify this data imputation by basically extracting the nearest neighbor in the training data set using the L1 distance, and then compute the entropy of the labels on that nearest neighbors. So you can basically see that our methods achieves the highest entropy here, while still remaining close to the training data manifold. So here, I should present you the test logical results, which is basically what people usually present in generative modeling. So here, I'm testing our methods against other benchmarks, including the adversarial VB case. So we actually found that for this small model, the VAE performs the best if you use the importance sampling methods to estimate the log likelihood. But in this case, you know that for other methods, you don't have a Q distribution that is tractable, so we need to train a Gaussian proposal to do importance sampling, and that Gaussian proposal is trained by Variational bound, where you fix your generative model and just maximize it using Q. So in this case, we get slightly worse results, but you can basically see that the effective number of sample size is much smaller than the VAE case, even when you simulate it with 5,000 samples. So we sort of think these results are not reliable, so we want to push it a bit forward. Then we basically replace the kind of Gaussian proposal trained by VI by the Gaussian proposal trained by IV. So this is kind of like an improved objective function that gives you a slightly better proposal distribution, and then we compute the importance sampling estimate using quite a lot of number of samples. So you can basically see that for different proposal distributions, the effective sample size numbers here are very different. And if you plot the kind of test logical results as a function of the effective sample size, you can see that basically our best model finally outperforms the VAE model. So we think that the evaluation for the generative models, especially for those with implicit model or implicit Q distributions, is a challenging task. So we are also investigating on the AIS estimation. So just to conclude, so I'm just presenting you a very flexible framework to do approximate inference, but maybe it's too flexible because I haven't actually figured out the best combination of the Q distribution of the Q architecture and the MCMC algorithm, and also the kind of update rule for the Q distribution. So, but there are also some other interesting things. First, when I simulated MCMC methods, I only use the samples at the last iteration. I basically throw away the samples from Q1 to Qt-1, but they also have information from your model. So maybe you can invent some kind of clever way to use them. And also, I think this method can be extended to discrete case if you can, say, amortizing the Gibbs sampling in the RBNs, then you can speed up training. And finally, in this case, I only consider models that has tractable log likelihood. In the case where you have intractable likelihood, for example, ligands or in ABCs, how can we extend this method to them? Okay, thanks.